Today, with great pleasure, I would like to introduce you to our Google Summer of Code interns, Niklas, Anastasiia, and Anshuman, who went through great lengths to join us for their sort of internship with DeepPavlov for the summer. It was a fascinating experience for us so far. Sometimes complex, maybe even complicated, because the problems that folks decided to work on are not really easy. But nonetheless, we enjoyed every single time we had a chance to work together, and we are very, very proud of what they achieved so far, and we want to share their progress with you through this community call and through the recording. And before I will pass the chance to talk to our GSOC students, I would like to use this opportunity to talk about our latest version of DeepPavlov library and what specifically is happening with it. So, like half a year ago, which feels like eternity ago, we launched 0.14 with new intent catcher and so on, and we promised to build version 1.0 of the DeepPavlov library. And the thing is, the road to version 1.0 is much harder than just changing the version number, and a lot of things have to be filled in and fit in together to build version 1.0, and we have decided to make a few more intermediate releases on our way to version 1.0. I'm proud to say that, by the way, contributions of our Google Summer of Code students will also become a part of 1.0 version of our library. And later this year, we want to run some kind of DeepPavlov conversational AI day. It will be held in spatial chat. It will be one-day event probably, and we will give lots of different talks about our technology, our latest contributions to the open source in terms of conversational AI. And before that, we still have to go through a couple of more releases at least. The one release we want to launch in the next few days, about 1 week, is 0.16. And in it, we are actually starting our great migration from TensorFlow, which we're very thankful for, to PyTorch, which became like the standard de facto across multiple AI solutions across the world. And we know that it was really painful for people to use the DeepPavlov library in their environment when it was not used as Docker containers, because you had to struggle with TensorFlow 1.x, and you had to struggle with old Python because we were limited because of TensorFlow with versions of Python like 3.7, 3.8, as far as I remember, and it was really frustrating. We know that. So we are making this transition, and we're making it, starting it right with version 0.16. And what's going to happen? In this release, we will ship some foundational models as new configs. Just to remind you, the entire DeepPavlov library is a set of configuration files that basically represent different ML models that we have in our library. And the basic models for NER and Squat, they are written in TensorFlow, and we are building new PyTorch models for them, and they will be shipped as new configs. So you will have probably about 1 month to make migration from from TensorFlow version to PyTorch, and be able to test them in your environment and see what's happening, how it works, what works well, what works not really well, and so on. And in a couple of days after that, we will publish a detailed blog post of the new release with full list of new models. And we will encourage you to test those models in your environment and provide us back the feedback on what went right, what went wrong. The important thing here is that this is, by the way, the models we're talking about, the base models, the base 7 models we have. The important thing is in 0.17 that we aim to launch by end of August is these new models, they will replace existing TensorFlow based ones. And obviously you'll be able to use them by simply migrating to 0.17. But those models will behave a little bit differently, obviously. And because those changes might be important for your environment, we encourage you to use 0.16 as a way to test these new models in your testing environment, maybe in production, and see how it could influence your product and your deployment. Small teasers, in 0.17, we will ship our updated version of GoBot. It will have support for raster 2.0 format of their files. It will finally have integration with intent catcher, which we promised like half a year ago. And it will also include new slot filling. And we also publish new tutorials and deep integration with DeepPavlov agent. So as you know, we have this multi-skill AI system platform. We call it DeepPy these days. We will call it Dream very, very soon. And it has an example of GoBot based skill in it. So we will update that build, that skill to use the latest version of GoBot. And I think more or less at last but not least, we will probably release or maybe talk about our another engine for building skills, this time for scenario-driven skills, and we call it DFF markup. It's a Python-based framework. It's something based on the idea of state machines. Its framework was born during our participation in competition Alexa Prize 4, and we used STDM framework from Emory University, who were winners of the last year's Alexa Prize 4, or sorry, Alexa Prize 3. We used that as an inspiration for us to build our own state-driven, scenario-driven engine for building skills. And we actually altered a lot whatever folks from Emory University have created. We removed almost everything they built in terms of their domain-specific language, and we decided to build our own one. It's Python-based, so there is no new specific format like the one you have in Brasa or what you have in STDM from Emory University. Instead, what you will have is simply sort of dictionary in Python with validated JSON schema. And in it, you will be able to describe the flow of your state-driven scenario dialog in the system. The difference between classic scenario-driven frameworks and ours is, in our case, you will be able to use the richness of our complex system, of our DeepPavlov agent with all of the annotators you have in it. And you will be able to use intents, you will be able to use different classifications like for motions, for toxicity, for black words, and so on. And this will make it easier for you to build scenario-driven skills using our multi-skill architecture. And if you don't need the whole architecture and you will need something more simple, we will also make a DFF markup available for you as well. Obviously, we will be limited with capabilities of the basic framework, but nonetheless, it will also help you to build simple systems. And as I said before, this is what will happen when we will release 0.17. We will rename our near and squad models. We'll remove the PyTorch word from them, and they will replace the models that we had in the library for like a couple of years now, if not more. And with that, I would like to introduce Niklas, who is going to talk about one of the fantastic additions to our GoBot framework. It's a completely new architecture for goal-oriented skills and chatbots, and I'm happy to introduce Niklas to you. Niklas, when we will start talking, and this also applies to Anshuman and Anastasiia, please tell a couple of words of where you study or where you work, your background, and so on before moving on to your talk. Okay?
All right. Thanks, Daniel. Let me just first share my screen, make sure everybody can see this. All right. So quick background. My name is Niklas, and I'm studying at Peking University right now, and working on natural language processing, NLP, and now at DeepPavlov in collaboration with some of you smart guys. And the big goal of all of this is, of course, solving the Turing test, and well, obviously also creating great chatbots. And so that's why I created this quick slide to give you sort of a an idea of the why, like why are we doing this? And chatbots can create a lot of value. Right now, often they're still sometimes very annoying on websites if you engage with them, but you got to try to see the bigger picture, like the potential that they have to, evolve into, agents that can really solve your problems, and even beyond that, become companions and friends in your real life, even though it often doesn't seem like that yet. And so, so here's just two quick examples of how chatbots can provide value right now. So on the left-hand side, you see an example of a chatbot querying you to add something to your calendar. And that's an often used function, and is often called like a goal-oriented chatbot, meaning that, there's a clear goal of, for example, you scheduling this meeting. And on the other side, we have chatbots which are more focused on casual chatting. And so these are sometimes referred to as chit chat bots. And so, there's not a clear goal. They just want to entertain you. And, you also have that mode in your local Alexa at home, where you can, go into conversation mode, right? And I think the hope is that eventually, or I guess the vision is that eventually they're going to merge, right? And you're going to have a chatbot that can do both. He can be very goal oriented, but he can also just chat with you if you want to. And and ideally, at a very high quality, indistinguishable from humans, which is what this refers to. All right. And so so what am I working on for with DeepPavlov right now? We're implementing a new goal-oriented model, so the more like closer to the left-hand example, called TripPy. And this is just a rough sketch of the architecture I made, where we have a user who utters something, and all these, the three below input fields, they're optional. They might not always be there. And then we process his. So this is then what happens in TripPy itself. As a user, you only see your own utterance pretty much. And then within TripPy, the input gets processed, and it gets fed into a Bert model, a Bert transformer. So within the processing, the text gets tokenized and turned into token IDs, which are then fed into a Bert encoder. And this Bert encoder is specifically adapted for dialog state tracking. So it outputs, essentially it outputs binary logits for each token in your input text. And these binary logits essentially mean as to whether the text sort of you inputted to it has any relevance to the slot values it wants to fill. So if we go back to this example here, a slot value on the left-hand side might be, I want to have a 10:30 a.m. meeting. And then so if the slot value is this kind of this time, 10:30, and we want to catch that in the input, because that's really important for goal-oriented bots, because they want to help you schedule a meeting, for example. So if, and your input is in that example you selected, but if, it's written input and there'd be 10:30 in there somewhere, then we'd want to, detect that. And so this is what these kind of ones and zeros stand for, which come out of the Bert for DST. And then what we do is we, first of all, and this is very different from the original TripPy paper, we decided to add a dense layer with a softmax, which predicts several actions for the chatbot to take. And then apart from that, we're having this kind of slot value position post processing, where in the slot value position, so that's like these 0 and 1s, and we gotta once we have them, we kind of post process them in order to then extract the text where it's a 1, and this text is then sort of turned into a slot filled dialog state. So you might imagine a slot name could be time, and then the slot value could be 11:30 a.m. right? And so that's sort of just tracked in a dictionary in Python, and together with the action index that we predicted up here from a set of predefined actions, we're feeding that through a database. And from that database, we give the database essentially all of the slots we found. So we say, for example, time 10:30 a.m. Location Paris, and then we check the results from the database, and the database might give us back, all right, meeting room 10 is available, or whatever the use case might be. And then this result from the database, together with the action index we've predicted, is fed into a NLG component, which essentially is a rule-based system to then construct, an output to the user. So we take this, for example, meeting room 3 is available, and action is something like some sort of predefined text. For example, this and this room is available, and we sort of merge that together, and then the response that comes back to the user is, thanks for your inquiry, room 3 is available, something like that. And then it goes back and forth, and again, fed into the model, like the next user input, and we keep sort of, that's what this refers to, we keep track of the dialog history and the previous filled slots, and try to have a valuable conversation for a user. All right, and with that, I already want to kick off into a demo, because else people are going to get bored. All right, and this is more exciting. So let's see. So I'm going to show you like even how you can do it yourself if you're interested in. So if you want, it's already public on my fork of the DP repository. But as Daniel mentioned, we're planning to merge this one also in the next release of DP. So you'll be able to access it via the main repository at that point. But for now, it's on my fork here, and we just go into DeepPavlov and examples, sort of to get a nice. There are 2 demos right now, and 1 more is coming, perhaps even 2 more. And then you can just open this in Colab. For now, this link is not going to bring us anywhere, because you just need to change the name here to the name of my repository, and then copy and paste that in. I already did that over here, and so that's exactly this Colab. And yeah, so let's just run it. Let me just connect to this. I'll make sure I'm on a GPU. You can also run it on a CPU, and you can even run it on multiple GPUs. So there's already the code for doing data parallelism in the TripPy model. But yeah, like either way is fine. On the CPU, obviously it'll be a bit slower, but that's fine as well. All right, and now let's just copy the repository. So for now, again, we're still copying the fork, cloning the fork, and getting some requirements. And here we're using a more updated version of the transformers library, but we're also planning to update it in DeepPavlov soon. So then we won't have to explicitly update it anymore. All right, and then next up, we get the data. So in this case, we're already using a restaurant data set from DSTC2, which is a yearly sort of challenge in that field, which releases new data sets and so on. And this is pretty useful to get started right away, because sometimes this data collection can be a bit expensive. And so here's a quick example of how the data set looks like. We get like a lot of, so here's one, let me see. So these are user utterances. So what the user would say, for example, and this is the text that the user is saying. So he's saying cheap restaurant, and then this gives us the slots. So in that case, the slot name is price range, and the slot value is cheap. And then it goes to the next text, any, but in between that is an utterance from the system, which is down here. And in that case, it just starts off with a welcome message, which is then this action. So this one here, the act here is the action index that later on we try to predict. So yeah, this is our training data. And yeah, now we just take a subset of that data, because in real life, data annotation is expensive. So we just take $50 here. And now if we have a database, we can build that one. So if we just quickly go back to the slide here, the database is optional. So you can also skip it, but then obviously you can't retrieve anything. So normally if you, for example, don't have slots, if you only want to have a conversation, you don't need any clear any slots like time, then you can just skip that and just go right into the generation. Yep, so we've got our database. What we did here is we iterated through that data and extracted the turns. And in that turn data, there's a field called DB result. So I don't know if we have that somewhere in here. Yeah, here. So this is an example of the DB result in the user utterance. And so here we just extract that from the training data and add it to our database, so that can later on be retrieved. All right, let's close that down. And let's do a quick example of a query. So now if we query the database, we get nothing, which is great. Let's just try this again. Perhaps the query is, all right, there we go. So now we put in the slot name, price range, slot value cheap, slot name area, and the slot value south. And then we get 2 possibilities for restaurants that correspond to those criteria. All right, but now the exciting part, training the model. And let me close this down. So yeah, so this is just some explanation you can read through if you want to take a look at the demo. Here again, the slide that we just took a look at. And now we got to go into configuring the model. And I'm putting these configurations here right in the code, so you can change it yourself if you need to. So you could, for example, change the data or the database. And down here, you can also play with the parameters for training. So, adapt the batch size, whatever you feel like, learning rate, so on. And yeah, but we're not going to go into training right now because it'll take about 30 minutes. So we'll just download a model that I've already, all right, let me check. I've got to quickly upload my Kaggle JSON. We're going to download a model I've already pre-trained. And yeah, so essentially I've just, executed this step, trained the model, uploaded it to Kaggle, and now we're downloading that model so we can save some time here. And you can also do that in the actual code. If you don't want to train it but just want to play with it, just skip to that step. All right. So wait for that, and we'll also skip evaluating training. So essentially, you're going to reach an accuracy of roughly 40 to 50%. Which and how to interpret this. So this is the interpretation of this is that if the accuracy is like it's correct if the model predicts exactly the same chain predicts the same change of system utterances as in the original data, which often is very ambiguous because sometimes there are 2 different actions. One of them is goodbye and the other one is see you next time, right? And both of those could be correct. So having an accuracy of about 40 to 50% is not necessarily bad in that case because there are about 40 actions. So the bot is still going to work fairly well. If you have less actions, you'll see that it'll be considerably better. All right, we've got the model, and DeepPavlov makes it super easy to play with it. So you literally just build it based on the config. And now we're downloading the original Bert transformer. And there we go. This is, we can also check out the architecture here. Let's just make sure it took the pre-trained model. Yep, it's at initializing TripPy from saved. So it took in the weights that we've downloaded. They're probably somewhere in here. Yeah, I think right here. All right, and now we can play with it. So let's kick off with, I've just prepared this dialog, which is also in the demo, because it's a good example of how it should work. And then I'll show you some, we'll play with it a bit on the bad side. All right, so we might start the conversation with just saying, you know, I wanna eat. Can you suggest a place to go? So let's kick this off. And the bot replies with, what kind of food would you like? And now notice that even though we finished this code cell, the bot is still, you know, it's still an active variable, and it has saved this conversation history, right? So right now in this bot variable, that conversation history is saved. And that's why whenever you start a new conversation, we, you know, reset the bot, and then it also internally resets all of its, you know, dialog history and all of this stuff we've seen here pretty much, except for the slot names. I mean, they're in the config, so yeah. All right, we might say, okay, perhaps something cheap. Let's see what we've got. What part of town do you have in mind? Let's say in the north of town. And he makes a call for us. So he now calls the database with almost all of the data we gave to him, and replies with Magna is a nice place in the north of town and prices are moderate. All right, so that sounds good. I like Magna. So we'll say, what's your phone number? The bot gives us the phone number, which is great. We'll ask for the address. He can give us the address, and because that's, he now has like loaded all the information from the database. So yeah, and by the way, you know, this text is not like hard coded, so we can, for example, just change something here. What's Magna's price range again? And he says the price range at Magna is moderate. All right, and then we say, all right, sounds good. Thank you. And he says, you're welcome. All right, that was a great conversation. And now let's try to set him off a bit. So I'll just copy this in here and start a new conversation. All right, he says, what kind of food would you like? And now let's explore some edge cases, right? So we could, for example, I don't know, try something really exotic. What about, you know, I want food from New Zealand. Right, so what happened? So he catched the correct food request, so New Zealand. So he catched that as a like sort of the food type we want and made a query, but he didn't find anything. All right, so I think that's still reasonable. And I don't know, let's see if we can now perhaps just change it and say, oh wait, let's just start a new one and do something a bit more tougher. What kind of food would you like? Let's say, let's ask him, what kind of food do you have? What kind of food do you have? And now he gets a bit confused because this kind of data is not in the training data. And so now what did he do? He did just a random API call with don't care for all slots, because he thought we just don't care because we didn't give him any actionable data on the question, what kind of food would you like? And makes this API call. I mean, he still gets us some results, so we could still say, all right, Frankie and Benny's, that sounds good. Great, I'll take that. But obviously it's not quite what we wanted, right? We wanted him to sort of give us an option of what he has. And that's, right, that's also not very informative. And we wanted the bot to give us, you know, a list of what he has. And, you know, he can only do as much as what's in the training data. So, you know, when you design your own bots, make sure you either have examples of that in the training data, or you know, provide some additional functionality for it to kind of, you know, catch these sort of weird requests, if that's something what, you know, your users might be doing. Yeah, let's just finish this conversation off and say, give me their address All right. Leisure Park, Clifton Way, Cherry Hinton. Sounds good. Great. Bye. And there we go. And lastly, real quick, just give me a couple minutes. I just want to let you know that you can also use Rasa configs. So you can now use Rasa 2.0 and hopefully soon, 3.x, which is, once it's released on the Rasa side, to define your training data. So here we have just some toy training data, stories.yaml for those who are familiar with the Rasa format and NLU domain. And we can write a config. Just make sure that you're using our Rasa dialogs iterator at DeepPavlov and install the requirements for TripPy. And then similar, we can just train it. Well, actually, we can, I don't know if we have a couple minutes left. Well, I'll just show you how it roughly looks like. And then you can, query it and it'll reply based on what it's seen in the training data. So this one isn't yet on the repository, but I'll add it very soon. And yeah, with that, that's pretty much it. I'm gonna head off to Cambridge Leisure Park, Clifton Way, Cherry Hinton now. And thanks a lot for listening. And I hope to, I hope you try them all out. Feel free to reach out if you have any problems. And yep. Thanks everybody. Thanks, Daniel.
Niklas, thank you so much for your talk. And tell me one thing about TripPy. How far do you think TripPy is from having
From having?
For example, our old RNN models that we used in GoBot's dialog policy for the last few years. So, what do you think is the most important difference?
All right. I think so. What TripPy improves on, it's generally faster. So if you have a small data set, you'll be about 50% faster with TripPy. In that case, I trained TripPy a bit longer. So for this data set, it took a bit longer than the original model, but generally it's going to be a bit faster for your data set. And then I think the biggest improvement with TripPy is that you'll see in the kind of text it catches. I don't have a comparison with GoBot here right now, but because of the the pre-trained BERT model it makes use of, it has some very strong priors of the language, so it'll catch more of those outliers. So let me just go back to some of the text we wrote here. So lots of those simple shortcuts. It'll just know what that kind of means because it has those pre-trained BERT weights. And yeah, I think that's one of the key advantages. And I think we can definitely still improve on it. I mean, these kind of things, implementing some sort of generative priors in it could be interesting, similar to the GPT style. But yeah.
I see.
Did that answer your question? Sorry.
Well, yes, in a way.
So speed and kind of, natural language understanding, I think.
Yeah, I understand that. It's just what I wanted to highlight is the biggest value for me personally of GoBot and different architectures and specifically different dialog policies is we have this big dream where you just give a couple of examples of dialogs to the system and it suddenly gives you magic after, I don't know, a couple of hours training on fast GPUs. And I mean, we still are far from the magic that we probably expect, but we are very thankful for your work and for your contribution to get us closer to that magic. Thank you very much, Niklas.
Thanks, Daniel.
Okay, so I think we can give a chance to Anshuman, and then we will end with our glorious Anastasiia to give her talk on relation instruction. Well, I mean, Anastasiia made a great talk yesterday in Russian version of our community call, so we already know how she is going to perform. but we are very anxious to know how Anshuman is going to make his part. And welcome, Anshuman. Tell a little bit about yourself before, and then move on, okay?
Yeah, sure. So
thank you very much, and welcome.
Yeah. So I'm Anshuman Singh. I'm a final year student at SRM IST India, and before joining DeepPavlov, I was working as a mentor at OpenMind, which is also an open source organization which works on privacy preserving machine learning tools. So with technologies like differential privacy, federated learning, those kind of things. So with DeepPavlov, what I've been working on for the past 1 month almost is multitask Bert. And let's see what my progress is. So first we should understand like what is really a multitask about. So I'd like to explain with a very simple example. Let's say you have a data set and it has a low number of examples, right? Let's say it has about 5K examples, and you train a BERT model on it, but you don't achieve the desired accuracy that you want on that data set. But there is another similar data set which you can also train on, and maybe you can use the knowledge that is learned from training on that data set to on the data set which is smaller in size. So this is kind of like sharing information between tasks that are interrelated, and it is kind of like doing it within a single model, so that the number of parameters used, hence the memory, is efficient than like coupling, like let's say 2 BERT models. And this can often also lead to better accuracies as compared to a single BERT model, as you'll see. So with DeepPavlov, I've been working with 2 techniques. One of them is Bert and Pal, and the other one is CMTL. CMTL, I will just start working with it, and it's training as we speak, but I've made a lot of progress on Bert and Pals, and let's go through it. So just a small explanation on how Bert and Pal really works is in the diagram you can see we have like these Pal layers, so which are like projected attention layers, or PALs, and these layers are task specific. So as you add more tasks, these layers are going to increase. So with the addition of these layers, what we really aim to have is a slight increase in the number of parameters, but we can train across different tasks and achieve a better accuracy with using less memory and training time and everything. So how training works in Bert and Pals. So this was slightly tricky to implement in DeepPavlov, but it's been done, and it basically trains proportional to the training size. For example, if like the example I gave where we had 2 data sets, one is small and the other one has a large number of examples. So naturally you would like to train more on the data which has a large number of examples and less on the data which has low number of examples, because that's going to be best to avoid overfitting and underfitting. So in Bert and Pals, we basically have a list of probabilities. These list of probabilities is proportional to the training size of the data. And then we basically make a random choice based on these probabilities. And the choice we make is known as the task ID. And this task ID is gives us, okay, like if it's the task ID is 1, we're gonna train for task 1. If the task ID is, let's say, 4, we're gonna train on task 4. So it's kind of different in a way, because normally in multitask models, you train on one task first entirely and then move on to the other one, whereas this one has you keep on switching between the task heads based on this task ID. So now let's talk about how it's implemented in DeepPavlov and the additions, the additional components that I've added, and how they basically work. So the additional components that I've added in the configuration file, they're basically 3 additions. One of them is the Pal-Bert iterator, which takes care of the task selection. As I explained in the previous slides, we need to have a task ID. So the iterator is really responsible for generating this task ID and then passing it down to down the pipeline. And then we have a preprocessor, which basically extracts this task ID from each of the task examples. And then we have a Pal-Bert model. So let's take a look at each one of them briefly. So in here, you can see the task iterator is basically a collection of multiple iterators. For example, you can use a basic classification iterator, or let's say a Hugging Face iterator, which is also built in DeepPavlov, and it will work with that. So it basically groups the iterators in one, kind of, and then you basically provide it with 2 other parameters, and then it passes it down to the chainer. What basically happens in the chainer is you pass examples based on each task, and when the iterator passes these examples to the chainer, each of these examples have task ID along with them, because if you're training on, let's say, 3 tasks, the chainer expects that you have 3 distinct inputs for each of the tasks. So to extract the task ID, what we basically do is we have this multitask Pal-Bert preprocessor. So the task of the preprocessor really is to extract out the task ID from each of those examples and give us the sentences of each task and the task ID. Then we can move on to the model. So this model is also very similar to the multitask model that is already existing. That was one of my goals, to kind of make it as similar as possible. So here also you define all the tasks. You define the number of classes. For example, if task 1 has 2 classes and the task 2 has 3 classes, you need to define that so that you can build a classifier with that number of output nodes. And then we basically have these 2 really important keys in here. One is in distribution. So what in distribution really stands for is input distribution. This basically determines that how many inputs that this model gets are associated to one task. So for example, you can see like the input to this is task ID, Bert features MRPC, and Bert features RTE. So we have specified that we have 1 for MRPC and 1 for RTE. So it it is going to understand that, okay, if we have a task ID first, then the next one feature is going to be for MRPC, and the next one feature is going to be for RT, and that is also similar in Y distribution, which is basically for the labels. Now we can move on to a small demo. So basically, it works like any other model that you have in DeepPavlov. Basically, you write a configuration file, and you basically train a model using that configuration. And here I've already trained this model, which is trained on 2 of the glue tasks, which are MRPC and RTE. And it's trained already, and we can make some predictions on it. So here we have one example each for one of the tasks. So the top example is for MRPC, and the bottom example is for RTE. So both of them are kind of for classifying whether it's an entailment or not. So MRPC has 2 labels. It outputs 0 if there is no entailment, 1 if there is entailment, and RTE outputs entailment if there is entailment, and if there's not entailment, it outputs no entailment. You can also notice we have something, we have -1 over here. So -1 really indicates the task ID that I was talking about. While doing validation, it really has no significance, because if we are going to validate, like prediction, we are going to predict on each of the tasks. So you don't really need to like provide this, and like just any integer would do fine here. So if we run this, you can see the output is 1, which indicates that yeah, there is an entailment in the first example, which should be true because they kind of say the same thing. And also in the second example, which is RTE, it also outputs entailment. And just to make things fun a little bit, let's have just switched around the second sentence of each of the tasks, and it should output the opposite now, basically. So yes, it outputs the opposite, which is 0 because there is no entailment, since both sentences are not interrelated at all, and the second example is also not interrelated. So now we can go back and we can discuss the performance, because multitask Bert is really about saving on memory for similar tasks and achieving better scores at the same time. So let's talk about performance. So for this experiment, I basically used 2 data sets from the glue benchmark. One of them was MRPC, and the second one is RTE. So MRPC has about 4,000 samples, and RTE has about 2.5 K samples. And I trained it on a batch size of 16 with a max sequence length of 128. So you can see there's actually a significant upside on the memory used, because if you train a single model with for each of the tasks, it is going to take about like 9,000 megabytes, whereas you trained one multitask model for combined, it's going to take about 6,000 megabytes. So that's about roughly about a 35% improvement on memory. And on top of all saving memory, we can train this faster, and it gives us better scores compared to a single multitask model. And so to train single models on let's say MRPC and RTE, it takes 15 and 10 minutes combined, 25 minutes for the multitask model, you can just train it in 15 minutes and you can achieve almost similar or better accuracy based on this. And now we can like compare the scores that I've achieved with the scores in the paper. So you can see the score for MRPC is roughly the same. But the score for RTE is quite low compared to the results in the paper. And this further proves like why multitask is important, because the model that I'm comparing it to was trained on all 8 tasks, and the 8 tasks also includes larger data sets like Quora question pairs, which has about 300,000 examples. So you get so it is possible that some knowledge that was learned from training on Quora question pairs actually helped improve the accuracy of RTE. So since I didn't train on Quora question pairs, I achieved the score which is better than a single model. But if I add more tasks to this model, it should do even better. So that is one of the points. This is what I really explained. Why the difference in accuracy? Since the data sets used are small to other data sets of Quora question pairs, has about 300,000 examples. SST has about 70,000 examples. So it's really about sharing the knowledge from larger data sets to smaller data sets. If you like train a singular models on both of them, you might achieve a good accuracy on the Quora question pairs because it has larger number of samples. But to achieve the same on some smaller data set, it might be difficult. But if you use this multitask model, which shares what it has learned from the larger data set, you can achieve better scores. So that was my presentation and my progress till now. It has been amazing to work with great people, and it has been a lot of fun. And I'd be happy to answer any questions if you guys
have. Anshuman, thank you so much for your talk. I was very, very pleasantly surprised with your improvements in the performance.
Yeah.
And in usage of memory, that was really fascinating. Dima, do you want to say something? Go ahead.
Well, I don't really want to say much. Actually, I admire the work Anshuman did, and I hope he will manage to do everything left. All in all, it was quite pleasant to work with him.
Yeah, basically Dimitri really helped me to like identify where I was making a mistake in the iterator. So kind of memory improvements can go to like his suggestions, and I changed that. It was actually quite simple to save about 2.5 gigabytes of memory just by removing some lines.
Yes, I recall that it was one of the ways to improve things, but yeah, the change is tremendous. And to everyone watching now, watching later, the cool thing about multitask Bert that Anshuman was working on and is still working on is you will be basically able to save a lot of resources on complex systems like our multi-skill AI architecture, because you will be able to bring multiple different classification tasks into the same component, like annotator in case of our DeepPavlov agent, and save your precious resources. We know that our friends at NVIDIA love you folks buying lots of GPUs and so on. But with growing complexity of our systems, for example, our DreamBot from last year, it used like, I don't know, maybe 8 annotators, maybe 10, and these days we have around 20 annotators, I think, something like that, and some of them are already combined. So that's a lot of resources. If one annotator uses Bert model, then it's like he's goodbye your GPU with 8 gigs of RAM. If you have a TI GPU with 11 gigs of RAM, so that's like a couple of models, and that means a couple of annotators. So when you want to host about 10 or 20 annotators, that's really small fortune you have to spend on your multi-skill AI assistant or a complex NLP pipeline. So what Anshuman is working on together with Dmitry Karpov is fascinating, and we are very, very happy to see this improvements in the performance.
I want to add one more detail. The implementation Anshuman did contains gradient accumulation, which is, to the best of my knowledge, absent in the original version of DeepPavlov, which is also great.
Yeah, thank you very much, Dima, for your comments. Anshuman, thank you so much, and we wish you the best in continuing your work, wrapping it up, and shipping it as part of the DeepPavlov library. We will be really thrilled to see yours and other folk components in version 1 of our library. It will be very, very big thing for us. Thank you very much.
Yeah, thank you for the opportunity.
We're very happy to host you with us. And now we are giving venue to our glorious Anastasiia Sedova. Anastasiia, please present yourself to the audience, and then the audience is yours. Thank you very much.
Yeah, hello everybody. My name is Anastasiia. Yeah, I'm a PhD student at the University of Vienna. It's my first time I taking part in Google Summer of Code, and really thrilled with this opportunity. And it's an really awesome chance to try to implement the relation extraction. That's what I'm doing. Okay, then maybe I shall start. So can you see the screen, or does it work?
We can.
Yep, we can.
Like this, it's the...
Wait. Nope. You're showing two screens at the same time. Yep, that's okay. The right way.
Okay, perfect. Okay, I'll try. Yeah, it works. So yeah, in DeepPavlov, I'm working on relation extraction for both English and Russian language, and that's what I'm going to present today. So to begin with, like, what is relation extraction? So relation extraction is a subtask of information extraction that deals with finding and classifying the semantic relations held between entities in an unstructured text. So imagine we have some unstructured text, just usual text, and we want to know whether there are some relations in this text between some words after all. So here is an example. If we have, for example, a sample sentence included Aeroline's domestic subsidiary Ostro, it's, for us as humans, it's obvious that these two entities, Airlines and Austral, are connected with the relation subsidiaries. Yeah, so our goal is to teach system to find these relations as well. The entities can be called just entity 1 or entity 2, head, tail, subject, objects. That depends on the system we are developing. The number of relation can be also defined for each data set and for each system. Okay, relation extraction can be classified like in different ways based on different properties. So first of all, like how we do it, how we teach our model to classify the relation. And the first maybe the oldest method, like approach to relation extraction, is a pattern-based relation extraction. And the idea here is pretty simple. We have some set of manually written patterns, which we check in our samples. So literally, if pattern occurs in a sample, it can be a sentence or a document, a text, part of sentence, couple of sentences. So if pattern occurs there, we state that this sentence, this sample contains this relation, and then we label this sentence with this relation. Okay, that's pretty simple approach, pretty straightforward. But with the development of deep neural networks, the different like really trained models can do stage. For example, it could be unsupervised relation extraction. So there are several methods of approaches as well for relation extraction that takes unsupervised text collection. That means like collection without any labels, and the model is trained on it to figure out which relations are held there. Another approach could be a supervised relation extraction. The difference from the previous one is that here we have a text collection with labels. So like in advance, we know in each sample which relation is held there and whether there is a relation at all, because for relation extraction we also need like negative samples where no relation is held, and sometimes we need them as many as the samples with some relation there. So that would be our input to the model, and that's exactly what we are implementing now in DeepPavlov. So we trained the model on a supervised data. Okay, that was about the how we train the model, but the relation extraction models also differ based on what their samples are. And here there could be sentence level relation extraction. That means that our trained model will try to find a relation in a sentence, so only between the entities that are in one sentence. But what we are doing actually is document level relation extraction. That means that in theory, the model can find the relation which is held between entities that are just somewhere in this document. So not necessarily in one sentence. So we think it's more usual and how it happens in real life, because it's often the case that especially when there is some document, like a couple of sentences that describe some event or some person, it's not necessarily the case that both entities are in one sample, right? In one sentence. So they could be spread across the document. Okay, but when we are talking about supervised document level relation extraction, a couple of problems arise. And now I'm going to talk about them. So let's have a look at this text. It's a text about John Stanistreet, who was a politician and was born in some city, Bendijo, in a family of his father and mother. He was elected to assembly and he was party member, and he died in the same city in the following year. Okay, imagine we have this document. It contains a couple of sentences, and we want to know which relations are held there. So the first thing that becomes obvious is that here there are a lot of entities, right? So they are highlighted with different colors. And yeah, in an ideal world, we want to have the relations between all of them, to understand whether they are related, all of them are related to each other. So that's really a tough problem, and it's called multi-entity problems. Actually, that there can be many entities in one sample. Also, sometimes the same entity can be named differently in different sentences, or in one sentence even. So, for example, here we have our text about this John Stanistreet, and well, in the first sentence, he was called by his full name, but after that he was called just by his second name, with his surname, because okay, yeah, why should we always repeat his whole name? And yeah, obviously we want our model to understand this this connection that John Stanistreet and Just Stanistreet are actually the same person, and it is the same entity, and all the relations that are valid for the first one are also valid for the second one. That's the second task we have. And okay, imagine we want to find the relation which is held between John Stanistreet and Bidijo. And yeah, we have them in the first two sentences, like he was born, like the second sentence, he was born in Bidijo, and also in the last sentence, he died in Bidijo. And what we have now, we have like the same entity pair, it's connected, like it's called different relations. Here, two of them. And it's often the case, actually, even in this text, yeah, the person can be born and die in the same city. Well, yeah, it's obvious, it's common, but it's quite tough for the model to figure it out. So here are the problems that that we deal with when we are talking about document level relation extraction. And now I'm going to tell how we solve them in our model. Okay, so as for relation extraction, DeepPavlov, from now on, my talk will contain two major parts. The first one will be about the model we used, so the document level relation extraction model, which is based on ATLOP model presented at the last year. And the second part would be about the data we trained our model on. And here are two corpora, one for English language and the second one for Russian language. So for English language, we use docred, and for Russian it was fullred. Okay, so let's begin with the model itself. So yeah, the model which we based our model on is ATLOP, so adaptive threshold and localized context pooling model. And essentially, the two major contributions of this model are adaptive threshold and localized context pooling. And I will begin with the second one, namely the localized context pooling. So the localized context pooling they propose in this model, like the authors propose in this model, is aimed at solving the multi-entity problem. That means that, yeah, in a document there could be multiple entities expressed with different tokens, different token sequences, and we want our model actually like to see the connection between all the entities in our document. And yeah, that's quite a common problem, and different models solve it differently. And very often it is solved by building a document graph. Yeah, when we just build this graph where we can trace all connections between different entities and yeah, trace it back and output the like what relations are found there. But if we are talking like about modern models, when we used pre-trained Bert, it doesn't really make sense to build some additional graph. We can try to use the information that is already encoded in Bert. And in this case, so the embeddings are often composed from different like entities. When we want to see which relations hold between two entities, we simply take the embedding of the first entity, the embedding of the second one, and we just compose it and say, okay, that's now the embedding of our entity pair. Okay, but here is the problem that some contexts of the entities may not be actually relevant. So if we look back at our example, and we still want to figure out the relation between Stanistreet and Bidijo, and yeah, how shall we do it when we just simply compose the two embeddings? We take the embedding of Stanistreet across all its mentions. That means the first one. Here we also had this mention, and this one. And well, the embedding of this entity in the first sentence is definitely relevant, and in the last one as well. But here in the middle, this embedding, like here, entity was mentioned in context of some election to an assembly or party, Well, it's not actually what we need. It doesn't contain the information that we need to figure out the relation between exactly this person and the individual. So yeah, maybe it's not actually the best solution to look at all entity mentions and all embeddings, and just simply to concatenate them. So what do they propose is the localized representation. So now we don't simply compose the embeddings, but we also enhance it with some additional local context embedding related to both entities. So here we use like directly the attention heads from the previous layer, and imagine here we want to have the context embedding for entities S and O, and we don't simply, okay, yeah, we take the embeddings from S and O from all mentions, but that's not the only thing that we take. We also take the information from the context, like the context of these two entities. And it also like it's a valid contribution to our final embedding, and then helps us to make it more accurate and more context specific, and after all, like better for exactly these entity pair. Okay, so the second part of this model is adaptive threshold, and it actually deals with multi-label problem. So in general, we always have a threshold, and with the help of this threshold, we convert the output probability of relation extraction classifier to relation label. So the classifier output is like a probabilities, and we want to know which relation we should output to the user indeed. And usually this threshold is a global, so it's global for all entity pairs, for all samples, and we just pick the value that maximizes the evaluation metric. Yeah, but actually the model may have different confidence for different entity pairs and classes. And in this case, the global threshold may not be an optimal solution, while a learnable one can be. So in this model, what we do, we introduce a new class, a new threshold class that is learned as any other classes, and so it learns this entity-dependent threshold value. So now the threshold value is dependent, and it's like different threshold values for different entity pairs. And during the training, the model pushes like all ways of like for classes that are positive. That means this relation is whole. They're like true classes above the probability of threshold class, and all others below this probability. And when we make prediction inference, the classes with higher lodges than this threshold class will become positive classes, and will be it will be our output. Yeah, the user will get these classes. So that's, yeah, and all others will be negative ones. So that is really very interesting approach. How could we output like different classes, more than one relation, but as we have already talked about, like it's often the case, and still like not output all of them. Okay, yeah, so basically we used this model, but we also made a couple of our improvements. So first of all, we added NAR tags as an additional input. Because like, yeah, this information is was in the data set we trained our models on, and we thought like, yeah, that's maybe a valuable input to the model as well. And also we add the opportunity to configure the threshold, because adaptive threshold is really a nice feature, but maybe some users want to set it up manually. So that can be done now in DeepPavlov. And apart from the model, like as for the data, we also add configurable amount of negative samples. So the model may be trained with different amount of negative samples, but like what allows like easy experimentations, training different models, trying interchangeably. And the amount of trained event test set can be also configured. Okay, that was all for the model. And now I'll proceed with the data we trained our models on. So the English relation extraction model was trained on DocRed. That's a data set from Wikipedia and Wikidata. And now it's the largest human-annotated data set for document level relation extraction. So the data there is labeled with also with entities that are labeled with narrow tags. There are 6 narrow tags overall, and there are 59 relations. So that's quite fine-grained classification. So here is an example from this data set. So here can you see like there is one sample that contains 5 sentences, and there are like different entities there, different entity mentions. For example, here is the one entity with like it was mentioned in text in 2 different ways. And also the object relation which is held between them. Also, there is information about supporting evidence, but we don't use it in training. So, and here is our statistics. As you can see, for training, we use twice as many samples as negative samples as positive ones. For def and test, it is the same, the equal amount. Okay, as for the Russian relation extraction model, we trained it on RuRed corpus based on the lenta.ru RU corpus. So it's actually sentence level. So the samples there are sentences. And here are more narrow tags, 29 narrow tags and 29 relations as well. So here is an example. You can see that here it's one sentence, and also it's annotated with like the entities are annotated and the relation which is held with them. Oh, and here is statistics, like the corpus is smaller and the proportion of positive and negative is basically the same. Okay, so to sum it up, how it works, how the whole system works, the inputs are now the tokenized data samples. So just a list of tokens, the positions of entity mentions, and the entity narrow tags. While the output would be the predictions of relation or like relations held in this document. And so that's how the whole system looks like, what happens inside. When we have this input, first of all, the data is pre-processed for relation extraction. So we encode the relation, we encode narrow tags, we turn them to one-hot encodings, aggregate also this mention. So if one entity mentioned across the document different ways, we aggregate it and recognize positions and so on and so forth. And then it becomes the input to the model. In the model, all this magic happens when we calculate the specific embeddings. We have a couple of additional layers, and at the final stage we have bilinear model, and then with a specific loss with this adaptive threshold, we get the extracted relations as an output, one or several of them. Okay, so here are the results of our experiments, and you can see that here is exactly the input I described. So the list of tokens, positions, and narrow text. And then, for example, for sample, Barack Obama has 2 daughters, Sasha and Malila. When we want to know the relation between Sasha and Malila, we can see that the relation here is sibling. And also the output is the ID of this relation from Wikipedia, from Wikidata, sorry. So yeah, and here are some results for Russian language as well. Okay, so far so good. But so it would be nice if we don't need to do this like narrow pre-processing somewhere in advance, and also like give this entity information as an additional input. And that's why we thought about triplet extraction, where the input could be a simple data sample, just sample, sentence, couple of sentences, doesn't matter, just string. And the output could be then predictions held in the document. And that's how this system looks like. So here we add this additional component named entities extraction, where we process the input sample and so tokenize it, find their entities, and also link it to Wikidata. Because like for our relation extraction, we want to have only the entities that are somehow mentioned in Wikidata. After that, like the relation extraction preprocessing also slightly changes because we like don't need to hear some stuff that we did before. But yeah, in its like most important parts is the same, and it's also an input for the model, and the output is also the same. And so here how it works. So yeah, imagine we have like this sentence: Barack Obama is married to Michelle Obama, and there is a string input just sentence, and we ask the model to find the relation, and it found quite valuable relation. So the entity Barack Obama was automatically detected, as well as the entity Michelle Obama, and the model had also found the relation spouse in between. And here also we have ID not only for the relation, but also for entities, because we have linked our entities to Wikidata. And that's how it works for Russian. Yeah, that was pretty much what I wanted to say. So I wanted to talk today, and thanks a lot for attention. If you have any questions, I'll be really glad to answer. Yeah, thanks.
Anastasiia, thank you so much for your talk today. I'm glad that we very soon will be able to provide these components to our audience. Last year, I've been super thrilled to see KBQA shipped as part of DeepPavlov library. It was like one of the first times someone ever built something like this and open sourced it. And your contribution is a very beautiful next step in our desire to make knowledge graph driven technology available for free for the global audience. And thank you very much for it. Thank you very much for your work.
Thanks a lot for helping me to do it, and for all your enormous like also involvement for everything that's we like all of us are doing, all of other interns as well. And it's really awesome to work with such an awesome team and really great people. So thanks a lot.
Yeah, it's very nice to know that this story turned so well. For the time being, we were really nervous about how Google Summer of Code is going to work for us. And just to clarify, the first time we ever participated in Google Summer of Code, and it wouldn't be possible without a lot of hard work by Oleg Serikov, who is here with us. He's leading Google Summer of Code program here at DeepPavlov, and without him, this would probably never happen. So Oleg, I wanted to say thanks, big thanks from me and from Mikhail Burtsev, who is currently traveling, so he wasn't able to join us today. And with that, I think we can conclude for the time being. Let me share back my slides about, yeah, wait a moment. Slides, where are the slides up? Here we go. Yeah. So just to wrap up, I wanted to say a couple of more things. Just to remind you that all of this great work is contributing to our conversational AI stack. It consists of 3 key components. We have our DeepPavlov library, which has lots of NLP components, and basically everything you've seen today is contributing to DeepPavlov library, our open source conversational AI library that started back in 2017 and which went through a great time of improvements and new development in all those years. And this year is phenomenal in terms of what kind of new functionality we are making available to the audience. We also have our multi-skill AI orchestrator, DeepPavlov agent, which is used by our Alexa Prize 3 and Alexa Prize 4 social bots, as well as by some of our customers. We also used it in the competition called ProChtenia, all about helping computers to better comprehend English language in terms of checking essays written by students in schools in Russia. And finally, not last but not least, we have DeepPavlov Dream, which is our platform for building multi-skill AI assistants. With it today, you can build goal-oriented skills with GoBot. And later this year, you will get an updated version of GoBot in library 0.17. And in library version 1.0, we will add TripPy architecture implementation made by Niklas. So it will be available to you. We also hope to give you some of the examples how multitask BERT built by Anshuman could be used to simplify usage of our annotators altogether on different data sets for different classification tasks, one annotator for multiple things. And that's going to be really, really awesome. And Anastasia's relation instruction will be available as one of the annotators for DeepPavlov Dream. And later this year, we will have a lot of work in this area. We will start open sourcing our Alexa Prize for social bot. We promised last year to open source our Alexa Prize 3 social bot. And as we just published our Alexa Prize 3 demo social bot to the public in last September, Amazon suddenly announced Alexa Prize 4. So we had to shift all of our resources to building our Alexa Prize 4 social bot. But this time, I hope we will find some time to publish our Alexa Prize 4 social bot to the public. And into it, we will add all of these amazing components built by Google Summer of Code students and make them available to you. With that, feel free to subscribe to our blog at medium.com. We will continue publishing blog posts there, and we have lots of blog posts about our experience in building Alexa Prize for social bot. Feel free to talk to us through our forum, our Twitter, and our Telegram group. Check out our DP and build your own multi-skill assistant with our technology. And with that, thank you very much for joining us today. And until next time, see you in the web.